Matthew. And so I'm going, this is not working. Darkness, okay. Okay, so I'm going to begin by talking about the kind of map of classical cryptography. We can place all cryptographic primitives on a map with primitives that can be built from each other downhill of them. So one-way functions are going to be below key exchange, since we can build one-way functions from key exchange, but we cannot build key exchange from one-way functions. Similarly, collision resistance is above one-way functions. Pseudorandom generators are on the same level of one-way functions. And secret sharing is information theoretically secure, and so is in the ocean downhill of everything, including one-way functions. Note that on this map, one-way functions are kind of special. And this is because they're very good for understanding this map, and looking at the relations is very useful for understanding the world of classical cryptography. But what exactly makes them so special? I'm sure you all agree with me that they're special, but why is this the case? Let's be a little bit careful. And the reason I like to think these are the case is because one-way functions satisfy 4 important properties. They are simple, minimal, useful, and flexible. By simple, I just mean that the definition is easy to state. A one-way function is a function that is easy to compute and hard to invert. By minimal, I just mean that one-way functions can be built from basically anything. They're downhill of essentially every cryptographic primitive. One-way functions are also useful. They can be used to build a whole bunch of cryptographic primitives. For example, everything in minicrypt. And finally, one-way functions are also flexible. And I'll use this as kind of a catch-all term to mean that one-way functions are very well-behaved and easy to work with, and give 2 examples. The first example is that one-way functions have a combiner. You can take 2 one-way function candidates, one good, one bad, smash them together and get a candidate that is secure, as long as either one of the 2 underlying one-way function candidates was secure. One-way functions are also very robust to how we define them. You can come up with many different definitions of one-way functions. For example, you could define the standard strong one-way functions, which cannot be inverted with all but negligible, with any negligible advantage. Or you could define weaker one-way functions, which can be inverted with all but inverse polynomial advantage. Or you could define distributional one-way functions for which you cannot sample from the pre-image space of the output. And it turns out that all of these definitions are actually equivalent in the sense that we can build each type of one-way function from the other. Okay, so that's great. But the question that I'm sure is all in your minds is, what about quantum? And so the setting of one-way functions is where we have a classical Alice and a classical Bob sending classical messages to each other. That is the classical outputs of the one-way functions, for example. But we could also consider having a quantum Qualis and a quantum Quab sending quantum messages to each other over quantum channels. And in this setting, we can also consider the map of cryptographic primitives. And in fact, it turns out that this map is very different than the classical map. In particular, key exchange falls into the ocean. And now there is something below one-way functions, in particular pseudorandom state generators or the quantum output PRGs. And we might wonder, is there a central primitive for this map as well? And it turns out there is. It's the EFI pair. At least this is the general consensus. It's still slightly controversial, but I think it's a pretty good candidate. Not only are EFI pairs, which I will not define here for this talk, but they're simple, minimal, and flexible. Trust me on this. And they can also be used to build a whole bunch of useful things, which is often known as microcrypt. Okay, so we have a central primitive for the fully classical setting. We have a central primitive for the fully quantum setting. And in this work, what we consider is a sort of hybrid setting between the two. The setting with classical computation and or quantum computation and classical communication. That is, we have a quantum Qualis and a quantum Quab running quantum computers, but the messages that they send to each other have to be sent over classical channels. And this is kind of like a near-term version of the quantum setting, since we are more likely to be able to build quantum computers than to be able to build quantum networks. Okay, so the focus of this work then is, what does the map of QC cryptography or quantum computation and classical communication cryptography look like? And is there a central primitive in the QC setting? Okay, so I'll begin by talking about some prior work. In fact, KT24 does define a candidate central primitive for the QC setting. the one-way puzzle. So Dakshita is actually the chair of this session. This is her work, as well as Kabir in the audience. And a one-way puzzle is very simple to define. It's essentially puzzle solution pairs that are easy to generate, but are hard to solve. So in particular, a one-way puzzle consists of two algorithms, SAMP and VAR. SAMP generates a puzzle with its corresponding solution, and VAR checks if the solution works. Since we're in the QC setting, the sampler is going to be a quantum algorithm, and we're going to require that the puzzle and solution pair are classical strings. Something that's slightly non-standard about one-way puzzles, but it turns out this is actually the right way to define it, is that the verification algorithm is allowed to be arbitrary and may in fact be inefficient. One-way puzzles satisfy two security definitions. They must satisfy correctness, that is, correctly generated puzzle solution pairs should pass verification, and they should satisfy security. That is, any quantum adversary given a puzzle should not be able to find a solution. Okay. It turns out that if you were to define the sampler to be classical, then these are equivalent to one-way functions. And this is because we could pull out the randomness and take that as the input to the one-way function. But in the quantum setting, since we aren't allowed to pull out randomness, this is not the case. And we cannot actually necessarily build one-way functions from one-way puzzles. Okay. So do one-way puzzles satisfy the important properties that I listed before? Well, I hope you agree that that definition was fairly simple. It took all of like 20 seconds for me to go over. And KT24 also gives some evidence that they are minimal. In particular, if we look at the map of QC cryptography, let's start with it covered in a deep purple fog. KT24 shows that we can build one-way puzzles from quantum output PRGs. And this actually means that the map of QC cryptography must look different from the classical map, at least. And furthermore, one-way puzzles can actually be built from basically any QC primitive that you can think of. And it's fairly easy to show most of these constructions, at least. So one-way puzzles are minimal. The next question then is, are they useful? KT24 also gives some answer to this question, and by showing that one-way puzzles can be used to build EFI pairs, and so therefore everything in microcrypt. And so, yeah, this is great. Woo, one-way puzzles can be used to build a lot of crypto. That's amazing. But there's something slightly unsatisfying here, which is that EFI pairs are a quantum output primitive. And if we wanted to say that one-way puzzles are a central primitive for QC cryptography, we would really like to be able to build a classical communication primitive from a one-way puzzle. And so prior to this work, at least, this question is open. And finally, we might wonder whether one-way puzzles are flexible. And since one-way puzzles are very new, not much has been studied about that for this work. Okay, so what are our major questions then? Are there any QC primitives implied by one-way puzzles? And are one-way puzzles well-behaved or flexible? And what do we show? In regards to the question of usefulness, our answer is going to be kind of. And I'll go into a little bit more detail about what I mean later. But in terms of flexibility, we get a strong yes. One-way puzzles are about as well-behaved as one-way functions, which is very nice. Okay, so before I get into how we go about doing this, I'm going to go quickly through how you actually build one-way puzzles from QC primitives, with the example of building one-way puzzles from QC signatures. So a signature scheme is a triple of algorithms, gen, sign, and versig. Gen outputs a signing key, verification key pair. Sign takes in a message and a signing key and outputs a signature sigma. And versig verifies whether the signature is actually a valid signature. And you should not be able to forge a signature without being given the signing key. Since we're in the QC setting, the algorithms generating the signatures in gen, sign, and versig should be quantum, but the signing key, verification key, signature, and message should all be classical. How do you build a one-way puzzle from a QC signature? It's actually fairly simple. The puzzle is just going to be the verification key, and the key or the solution is just going to be a valid signature. Verify will then just run versig, and that's the entire construction. It's that simple. Note that there's one thing I want you to notice about this is that in the definition of one-way puzzles, we only required that var was inefficient. But this construction actually is totally efficient. Var-sig is an efficient algorithm. And so what I've actually just shown is that we can build efficiently verifiable one-way puzzles, or EV one-way puzzles, from any QC signature scheme. And it turns out that this actually generalizes, and efficiently verifiable one-way puzzles can also be built from most QC primitives. With the notable exception of commitments, we don't know how to build EV one-way puzzles from commitments. It's an important exception. I'll come back to it again later. Okay, it turns out also that efficiently verifiable puzzles themselves are indeed useful, at least somewhat, in the sense that we can build at least one-time signatures from efficiently verifiable one-way puzzles. I'm not going to go through this here, but for those who have seen Lamport's scheme, it's essentially just that. Okay. And so what do these two facts mean for normal one-way puzzles or inefficiently verifiable one-way puzzles? Well, they say that essentially it's a necessary and sufficient condition for one-way puzzles to be useful to have one-way puzzles imply efficiently verifiable one-way puzzles. So if we want one-way puzzles to be useful, we should really have this. And do we have this? No. No, we do not have this. And in particular, we give a black box separation of efficiently verifiable one-way puzzles from one-way puzzles. And the proof of this is essentially 2 lines. First, we know from prior work that one-way puzzles can exist, even if the QP equals QCMA, which is essentially a quantum or QC version of P versus NP. And similarly, efficiently verifiable one-way puzzles can be broken using a QCMA oracle. And this is just by simple search decision, which is slightly more complicated in the QCMA setting, but that's the entire approach. Okay. So what does this mean for this question? Why do I say sorta? Well, one-way puzzles are not that useful in the QC setting, but efficiently verifiable one-way puzzles are. Its neighboring cousin are. In terms of flexibility, though, we do manage to build a combiner for one-way puzzles and define several variants of one-way puzzles. So for example, distributional one-way puzzles, weak one-way puzzles, strong one-way puzzles, and show that they are all equivalent. And we also manage to do the same thing for efficiently verifiable one-way puzzles. So efficiently verifiable one-way puzzles and one-way puzzles are both simple, minimal, and flexible. And the only kind of lack of one-way puzzles, or inefficiently verifiable one-way puzzles, is the fact that they're not that useful in the QC setting. Note that, again, there is this major exception of commitments. Okay, so what does this mean for the map of QC topography? Well, should we still consider one-way puzzles to be a minimal primitive? I still think that we should care about them a lot because they are really more minimal than efficiently verifiable one-way puzzles. We know how to build them from commitments and pseudorandom states. We don't know how to do this for efficiently verifiable one-way puzzles. But whenever we're talking about central primitives, whenever we're working with one-way puzzles, we should just always keep in mind efficiently verifiable one-way puzzles. So my kind of thesis here is that the central primitive for quantum cryptography or with classical communication should be both of them. Okay. So I'll finish the talk by talking a little bit about how this one-way puzzle amplification works. Surprisingly, parallel repetition is not enough. It's actually a lot harder than that. In particular, we know that we can amplify soundness for 3-round protocols in the quantum setting using parallel repetition. And one-way puzzles are a 3-round protocol, but they're not an efficient 3-round protocol. And so since they are inefficient, parallel repetition actually doesn't work since the reduction actually needs to run the protocol itself. Note that this does mean that parallel repetition does work for efficiently verifiable one-way puzzles. Okay, so what is our approach? Well, we again take inspiration from KT24, which builds something that's kind of like a PRG for my one-way puzzle. In particular, it's called an EFID, using the techniques of Hill, which builds PRGs from one-way functions. And so if this approach were to also work for a weak one-way puzzle, then what we could do is, since one-way puzzles are minimal for quantum cryptography with classical communication, we could just very easily build a strong one-way puzzle from this kind of PRG and get the full argument. Note that there is one major subtlety here, which is that the construction of the kind of PRG requires logarithmic advice. The construction needs to know the entropy of the one-way puzzle. But But this can be managed due to the fact that we've built a combiner for one-way puzzles. And so each value of the advice gives a candidate strong one-way puzzle. And so just combining them all together gives a fully strong one-way puzzle. And so this would be great if Hill did indeed work for weak one-way puzzles. But it doesn't. And kind of the very quick intuition here is that Hill requires using Goldreich-Levin to extract logarithmically many bits of pseudo-entropy or bits of randomness from a one-way function or a one-way puzzle. But if we only have weak security, then Goldreich-Levin is only guaranteed to be able to extract one bit of randomness, or perhaps even less than one bit of randomness. And so what do? Well, we just use a more modern approach of building PRGs from one-way puzzles. We replace Hill with Varangian 2012, which is just a different approach to build PRGs from one-way puzzles. And it turns out that if you're careful with playing with parameters and quantizing everything properly, you can actually build these kind of PRGs from weak one-way puzzles, and this whole approach will work. Okay. And so so this is great. We can build strong one-way puzzles from weak one-way puzzles. How do we build strong one-way puzzles from distributional one-way puzzles? Well, it's just exactly the same. Turns out that VZ12 also works for distributional one-way puzzles with no extra work. And so we get that strong one-way puzzles and distributional one-way puzzles are equivalent, essentially for free. I'm going to talk a little bit now about some additional results that we achieve. Note that this is the map that I've been drawing before. There's been this purple corner in the top right that I've been hiding. And that purple corner in the top right is pseudorandom states or quantum output PRGs with short output. Our argument before can essentially be used to show that pseudorandom states with long output cannot be used to build efficiently verifiable one-way puzzles. But pseudorandom states with short output through other works, we can use them to build efficiently verifiable one-way puzzles. And so what this means is we actually get a black box barrier for building pseudorandom states with short output from pseudorandom states with long output. Note that this observation was made through separate channels by two concurrent works, but it is actually the first black box separation between truly quantum primitives, at least that I know of. Finally, since we are essentially running through a different version of Hill, we're replacing Hill with VZ, our construction can also be seen as a cleaner or more classical friendly way of building EFI pairs or microcrypt from one-way puzzles. Okay, I'm going to end on some open questions, or three open questions I think are important. The first is this exception that I've been talking about this whole time. Can we build, what about QC commitments? So my question is then, can we build QC commitments from one-way puzzles? There's no barrier here, but I have no clue how to do it. Seems kind of hard. Second, could we build anything else in QC? Maybe there's other things like commitments that we could build from one-way puzzles. I'm not sure. Maybe. This is an important question, I think, though. And finally, for efficiently verifiable one-way puzzles, we showed how to build one-time signatures from them, but can we build anything else? Are they more useful than what I've said? Thank you.
Thank you so much. Do we have any questions?
A quick question. Do we have any conjectured examples of one-way puzzles that are not one-way functions?
That's a really good question. There is one that I know of, which is you can build pseudorandom states by taking like a random quantum circuit, essentially, and just evaluating it on zeros. And you can build one-way puzzles from pseudorandom states. This would not give a one-way function, as far as I know, but it's very conjectural. It's still a very new area.
Okay, let's thank the speaker again. So our next talk is on secret sharing with certified deletion. This is by James Bartosek and Justin Reyes. And we have Justin Reyes giving the talk.
I'm supposed to steal the microphone from you? Yes. Or is it just that? Oh.
Your life.
All right, thank you very much. All right, thank you for the introduction. Pop quiz for everyone. So you've got some data, you want to store it, but you don't want to store it yourself, and you don't trust the storage provider. What do you do? As cryptographers, hopefully the first thing that pops to mind is secret sharing. You take your secret and you split it into many shares and give each storage provider one of the shares. In general, if some unauthorized set of storage providers attempts to steal your data, they get no information. But if you have enough storage providers come together and give you the data, then you can reconstruct what you have. So here on screen, we have a scheme where any 3 parties are authorized. And so if 2 storage providers decide to betray you and try to steal your data, we get security. On the other hand, the problem here is that data breaches are very common. So over long periods of time, the assumption that only 2 providers will be compromised might not really be realistic. In this work, so as soon as the 3rd share is compromised, security is just completely lost. In this work, we asked the question of whether or not you can achieve security against an adversary who can eventually corrupt authorized sets of shares. So in particular, maybe they can eventually corrupt every single share. In the classical setting, there's not really much that we can do about this because classical shares can always be copied. So the adversarial storage provider can maybe store a copy of your data, and then when you cancel your subscription, they sell it. But interestingly, in the quantum setting, Broadbent and Islam showed that quantum mechanics enable certifiable deletion of secret information. And in fact, some prior works have studied a more limited form of secret sharing with certified deletion, where there are 2 shares and you need both to reconstruct. Let me be a little more specific what I mean by secret sharing with certified deletion. The scenario I'm considering is we have a classical secret that we're going to split into many quantum shares. Then there's some destructive measurement that you can perform to a share that will delete all information in it and make it useless if you want to use it for recovering the secret. So now with this tool, you can give out all of your shares to the different storage providers. And when you want to cancel your subscription with some storage provider, or if you suspect them of having a data breach, you can ask them to delete your data. And if they give you back a valid certificate, then you know that your data cannot have been sold or otherwise leaked. In this work, we have 3 main contributions. The first one is a general definition of certified deletion for secret sharing beyond simply the 2 out of 2 access structure. We also give constructions for each of the actually 2 different definitions that we're going to give. And as a general tool that we use to construct these, we give new high-rate randomness extractors for certain quantum entropy sources. For the rest of this talk, I'll start by going over the 2 different definitions. We have a no signaling definition as well as an adaptive definition, and I'll get into the differences between these in a little bit. I'll also talk about our adaptive construction, which is the most technically interesting part of the talk, of our work. And then also, I'll give a very brief security intuition for this construction. And finally, I'll list a few open problems in this area. All right, before we go to the definition of secret sharing with certified deletion, let's start off with some inspiration from encryption with certified deletion. Here, the adversary is given some encrypted quantum message, and they're going to delete it by producing a valid certificate. Then, after they've done this, they get the secret key, And even given this secret key and unbounded computation, they cannot guess whether or not the message was M0 or M1. Okay, this is nice and simple. And let's see if we can generalize this to secret sharing. A very natural approach is we're going to start off by splitting our data, and then the adversary gets access to some set of shares shown here on the left of the wall, and the rest of the shares on the right of the wall are not accessible to them. This is very similar to how we would have a ciphertext and a key in the encryption setting. The adversary deletes some of the shares, and then the wall comes down and they get access to everything. Nice and simple, very close to the previous definition. The problem with this is that it's not meaningful for all access structures. For example, if the stuff on the right of the wall was already authorized on its own, then it's meaningless for the adversary to delete the shares from the left of the wall, because as soon as it gets the stuff on the right, it just gets the secret immediately. To deal with this, we introduced two different definitions of secret sharing with certified deletion, which capture different kinds of adversaries. In no signaling certified deletion, we capture a sort of fast but distributed adversary, whereas in adaptive certified deletion, we capture an adversary which is a little slower, but more insidious and takes its time. Let's start off with no signaling certified. Oh, I'd like to mention very quickly that these two definitions turn out to be incomparable. I'd like to start off with no signaling certified deletion. To begin with, you can imagine splitting your secret into some number of shares. And now the adversary partitions these shares into unauthorized sets. So here, any 3 shares are authorized, and the restriction on the adversary is that no partition can have 3 shares in it. Now the adversary operates on each part of these, each partition separately. You can imagine this as a multi-part adversary where the different parts can be entangled, but they're not allowed to communicate. They delete some number of shares without being able to communicate. And if the remaining shares, share 5 and share 1 up here, are not authorized together, since there's only 2 of them, they get to combine their views. And the security requirement we want is that the final view, the final combined view, should be independent of the secret. So more specifically, it should be statistically close between the secret being S0 and S1 for any S0 and S1. Our first result is that there does exist a secret sharing scheme with no signaling certified deletion security for any monotone access structure S. A monotone access structure is simply a set of sets where a set of authorized sets, where if a set is authorized, then any superset of it is also authorized. Now let's move on to adaptive certified deletion, which is our second definition. The setup here is slightly different, although it does, of course, start with splitting our secret into many shares. At the start of the experiment, the adversary does not have access to any share. Over time, it can do one of 2 things. It can corrupt a new share, or it can delete a share. The adversary gets to keep doing this for as long as it wants, with one restriction. The constraint is that it's not ever allowed to control a set of shares which is not deleted and is authorized. So here, if the adversary were to corrupt another share, it would control 3 undeleted shares, and this would immediately reveal the secret. So the only option that the adversary has in this case is to delete something. And the adversary can keep doing this and eventually gets the opportunity to corrupt every single secret or every single share. The security requirement that we want is that the adversary's view at the end of this experiment is statistically close between any 2 secrets S0 and S1. Our second result is that there exists a threshold secret sharing scheme with adaptive certified deletion security. I'd also like to mention that there's an optimization for our construction, where you can actually create the sharing by just doing single qubit operations. Now let's discuss the construction of it. Before we get to our exact construction, let's go back to prior works and see if we can find any inspiration there. In prior works, they constructed a scheme where you split a classical secret into a quantum share and a classical share. If the adversary gets the quantum share and then deletes it, then even after they get the classical share, they still can't determine what the secret is. I'd like to note that the only share that can be deleted is this quantum share. The classical share, of course, because it's classical information, cannot be deleted. All right, let's see if we can use this as a black box. And in fact, our no signaling construction actually does do this. But it's not so easy for the adaptive case, precisely because the classical share cannot be deleted. And in fact, there's actually an adaptive attack on the no signaling construction, which I won't unfortunately have time to get into here, but happy to discuss later. Let's see why this classical share is really necessary and what the issue is with just leaving it out. So first, in Bartuszek and Khurana's scheme, the quantum share consists of some number of data positions and then some number of check positions, where the check positions just store some dummy information that's only used for verifying certificates. If you knew where the data positions were, then you could extract the information and reconstruct what the secret was. Of course, without it, then you're getting some random errors that are just noise and you can't get the secret. So in order to extract the information, you need a mapping of where the data positions are. And given these, now you can extract the information and recover. The issue here is that this is necessary for decoding your secret, but you can't delete it because it's classical. So we end up with a sort of conundrum where if we could protect this mapping theta, then we could get secret sharing with certified deletion, adaptive certified deletion. But in order to protect theta, we need secret sharing with adaptive certified deletion. Our key insight is to have an approach where we can reconstruct without knowledge of the data indices. To do this, we're going to use techniques from Shamir's polynomial secret sharing, which turns out to have good error correction properties. So to start off with, we have some polynomial f, where f of 0 is our secret. Then each share will consist of some number of evaluations of f. And these are mixed randomly with some number of check positions, which are just random Fourier basis elements. Now, the nice part about this is that if you measure in the wrong basis, and keep in mind you don't know which positions are which, then you destroy the information there. So if you accidentally measure a check position in the computational basis, trying to get information out of it, then you're going to destroy your ability to pass the checks and pass the certification. And if you accidentally measure a data position in the Fourier basis, then you similarly destroy the data that's contained in it. The nice part, though, is that if you do measure in the right basis, then the result of the measurement is deterministic. So to delete something, you simply measure everything in the Hadamard or the Fourier basis. And then to verify this, you can just check the check positions match. Everything else will be random. Now let's move on to construction or reconstruction. Here we have some number of randomly distributed check positions. And these are essentially going to be random errors whenever you measure it in the computational basis. Luckily, though, if you have enough points on the polynomial, you can simply reconstruct and correct these errors. And we can actually tune the parameters so that any k-1 secret shares don't reveal the polynomial. But if you have k shares, then you can correct all of these errors that are present in k shares. Now let's very briefly discuss the security intuition. First, I'd like to take a slightly different viewpoint where you are lazily preparing the shares. So the challenger here, as shares are corrupted, is going to first sample some random points. And the first 2 shares, let's say, where 3 shares are authorized, don't yet determine the polynomial, so we can sample them uniformly at random. Before the adversary gets its 3rd share, it has to delete something. And then the 3rd share contains some redundant information, so we have to interpolate it from the previous values. And we can keep doing this to get the rest of the shares. Now let's go back and argue that each of the shares looks uniformly random to the adversary. We're able to show that when the adversary deletes something, its knowledge of that share, it loses most of its knowledge of that share. So the challenger's copy of that share becomes high entropy in the adversary's view. Then we show that polynomial interpolation is actually a very good extractor for this source of entropy. In the last minute or two, I'd like to mention a few open questions. First, can we get adaptive certified deletion for general access structures? We only did this for threshold structures. Second, is there a stronger definition that captures both distributed and adaptive attacks and a construction that matches? Remember that I mentioned that our 2 definitions are incomparable. There's also the question of public verification. It's been pointed out to us after we released the paper that our no signaling construction can be generically modified to do this, but it's not clear how to do this for the adaptive construction. There's also the question of other threshold primitives, such as threshold signatures, where a number of parties who have a share of this signing key can come together to sign a message. But if you're kicked off the board of trustees, then you are forced to delete your signing key, and you can no longer do this. One last question is if we can get high rate commitments with certified deletion. This would perhaps use our new high rate randomness extractors, but there are some non-trivialities to this. Thank you all for listening.
Thank you for the talk. Do we have any questions from the audience? Okay, I have one quick question. For the case of public verification in secret sharing, is it plausible that this can be done without assumptions, or does it seem like one would need computational assumptions?
So in general, for public verification, you're going to need some computational assumption, because otherwise you could simply attack the verification key in order to find a certificate that would pass.
Yeah, that sounds plausible. Thank you.
Yeah.
Okay, let's thank the speaker again. So our next talk is a 2-way merge of the following 2 papers. Unconditionally secure quantum commitments with pre-processing by Luovin Qian, and unconditionally secure commitments with quantum auxiliary inputs by Barak Nehoran, Tomoyuki Morime, and Takashi Yamakawa. We will have Barak and Luovin give the talk.
Okay. So yes, I'm Barak Nehoran, and this will be a merged talk from 2 concurrent works, as Dakshita mentioned. The first is my own with Tomoyuki Murimai and Takashi Yamakawa, and the second is by Luovin Qian, who is also here and will give the second half of the talk. To start out, I'd like to dispel a common misconception about the words unconditionally secure. In the title, unconditionally secure is often used interchangeably with information theoretic security, but these are not in fact the same. And for this talk, it's crucial to understand the distinction. Information theoretic security, as opposed to computational, indicates that you're secure against any adversary, supposedly because the adversary just won't have enough information. And this is nice, of course, in many ideal scenarios, but it's not always possible to achieve. Sometimes we have to settle for computational security, where we choose some specific type of adversary that we deem to be efficient, and we show that this particular adversary can't break our security because of its limited resources. Now, the proof of security can take one of two possible forms. We could have security reduction, where we only show security holds conditioned on something else being secure. Or, in the best cases, we can prove security outright with no conditions. And nearly all security proofs fall along the diagonal of this table, either an unconditional proof of information theoretic security or a conditional proof of computational security, where we choose a specific adversary and show the security reduction to hard problem. And this is why the term unconditional security is so often confused with information theoretic security. And in fact, it's hard to find examples of any schemes that fall outside this diagonal. Security proofs up here exist, but are quite rare, and usually not necessary. On the other side, if we could prove the security of any computational cryptography, that would bring it down here. But unfortunately, there are barriers to doing this, and computer scientists have struggled to get around them. For classical cryptography in particular, this would require showing that P doesn't equal NP. And so we do have things like the existence of hard to commute functions, which are proven by a counting argument, but nothing cryptographically useful. So can we get unconditionally secure computational cryptography? Our works show for the first time a commitment protocol that falls in this category, specifically when all the parties receive a quantum auxiliary input. Commitment schemes allow someone to lock away a message that they can then send to someone else. And then later, they can reveal the message without being able to modify the committed message. Commitments with a quantum auxiliary inputs were first defined by our work in 2016 and allow all parties to receive a quantum advice state as input. The CKR construction showed security from a computational assumption. We show, perhaps surprisingly, that no computational assumption is needed. In other words, that they exist unconditionally with computational security. And to the best of our knowledge, this is the first example of a cryptographic protocol whose security is inherently computational, but yet is unconditionally secure. In the quantum case, commitments in the most basic form look something like this. You have two quantum states representing a commitment to either 0 or 1. And each state is on two registers, D and C, that are entangled to one another. The C register is like the locked box containing the message, and the D register is the key to open it. So now say that Alice wants to commit the bit 0. So she chooses the first state, and she sends the C register to Bob. And that's called the commit phase. And then later on, when she wants to reveal her commitment, she sends the D register to Bob, at which point he can see what was committed to, and he can verify that it's valid. The security is all about what happens in between the two phases. And hiding says that in Bob's view, he cannot tell whether Alice committed to a 0 or to a 1. And binding, on the other hand, says that Alice cannot act on just her view to change her mind about which one was committed to. I mentioned that we show a kind of quantum commitment whose security is unconditional, but computational. But why not have statistical security? Well, that's because even in the setting, commitments cannot be statistically secure. To see why, suppose that the two possible states in Bob's view are statistically close. So the commitment is statistically binding. Then there exists an operation, a local unitary, which converts the zero commitment to a one commitment, allowing Alice to cheat and break the binding security. So if you want a secure commitment, we need a loose one of either hiding or binding to have only computational security. But this doesn't actually prevent us from showing the security unconditionally. And in fact, for quantum commitments, classical barriers don't rule this out. To see why that's significant and to put it in context, let's zoom out to the big picture on computational cryptography. Classically, it looks something like this, with the implications between all cryptographic primitives, all leading to one-way functions at the bottom and everything equivalent to them. Because of this, the existence of one-way functions was considered the minimal assumption without which cryptography couldn't exist. And having secure one-way functions at least requires that P doesn't equal NP. In the last few years, however, a line of works on cryptography with quantum states has shown that this is actually not the full picture. And there is, in fact, a whole world of quantum cryptography below one-way functions, which may exist even if P equals NP, all leading to quantum commitments at the bottom and everything equivalent to them. Back in the 80s, when it was discovered that the quantum key agreement could be made statistically and unconditionally secure, there was hope that we could do the same thing with other quantum primitives like commitments. Of course, as I mentioned, we know that quantum commitments can't be statistically secure, but there might still be hope of proving unconditional security, since it won't imply that P doesn't equal NP, and so the classical barriers aren't necessarily an issue. In our proof that this is possible when all parties receive quantum auxiliary inputs, notably despite the classical barriers, may give us hope that we can do this in the standard setting as well. And now I'll hand it over to Lowen.
We're gonna do some picture share. Right. Right. Can everyone hear me? Okay. Yeah. So thanks a lot for Barak for introducing the background and the motivation for this. And for the rest of the talk, I'm going to basically tell you slightly more formally about the what we achieved. Okay, so again, this is the setting of quantum auxiliary input commitment. But before I talk about quantum setting, let me first remind you the classical setting. So actually, classical auxiliary input cryptography is something that was already studied like back in the 90s. And in the case of having a commitment, what that means is that each party can do some possibly inefficient pre-processing. And at the end, they'll obtain some short bit string that they can hold on to. But it's crucial that this bit string is actually independent of whatever the input that you are going to use for the actual scheme. Yeah, so each party does this, and then in the end, they hold on to this aux bit string. And actually, here it is pretty like there is a folklore result that even for commitments with classical auxiliary input, the P versus NP barrier still applies. By which I mean that if you can construct such an auxiliary input commitment, it will still imply P not equal NP. Okay, yeah, I should emphasize here that we, of course, should allow the adversaries to also be non-uniform. So they can also do arbitrary pre-processing depending on the scheme. Okay, so what do I mean by quantum auxiliary input commitment? It's just classical auxiliary input commitment, except that everything can be quantum. So at the end, they can hold onto some quantum state without loss of generality. Let's think of it as a pure state. Everything else is the same, except everything can be quantum. Okay, so now let me state our main theorem more formally. We show that unconditionally, there exists a quantum auxiliary input commitment scheme that has inverse exponential security error that satisfies the following security. First of all, it's statistically binding, so it's secure even against unbounded committer or Alice. On the other hand, it is computationally hiding with that inverse exponential security error against all exponential size receiver or Bob. So you can think of it as any exponential size quantum circuit with exponential size quantum auxiliary input. This is unique to my work, where we further show how you can get this piece of auxiliary input with pre-processing. So more specifically, I show that you can prepare this auxiliary input in at most doubly exponential time. And if you are willing to let the parties communicate, you can reduce this doubly exponential time down to a single exponential. Alternatively, you can assume BQP equals QMA, in which case you can also do this with single exponential time. So this is actually okay here because the security is unconditional. So I can assume whatever we know is consistent with our understanding of complexity theory. Okay, let me first address a quick concern that you may have, which is that, okay, if the pre-processing in order to get this piece of quantum state takes exponential time, does this mean it is completely irrelevant for if I want to use this in practice? Well, actually, because our scheme has an excellent exponential security, you can maybe just pick a smaller security parameter. So for example, 48, then maybe you can just take 2 years to find this quantum state. And maybe that's okay. Maybe that's a good price to pay for unconditional security. Okay, another concern that you may have is that, okay, as Barak mentioned, there are many things that we can do once we have a quantum bit commitment scheme. Is it also true that we can do those applications if we only have a quantum auxiliary input commitment? And the answer in our work is yes. There are some small subtleties, but basically the previous construction mostly carry through. So in their work, they show that you can get zero knowledge proof for NP, although you need to add all the suitable quantifiers for quantum auxiliary input. But I think it's still a very meaningful notion of zero knowledge. And in my work, I show that you can actually go all the way to secure multi-party computation with simulation security, although there are 2 caveats. One is, as before, we need quantum auxiliary input, and the simulator also needs to have access to this quantum state, but that's actually independent of the input. On the other hand, we only get epsilon simulation security instead of negligible, but it's still good enough for most applications. Yeah, you should. I'm not going to explain these in detail, but you should take a look at the paper if you're interested. Okay, so now let me actually tell you how we construct the quantum auxiliary input commitment. And the nice thing about this construction is that it's actually pretty straightforward, that I can fit the entire construction in a single slide with reasonable font sizes. Okay, so let's begin by considering some good classical function mapping lambda bits. Lambda is the security parameter to 3 lambda bits. And for some, so we'll use some function, and in particular, I'm going to pick a good function for some definition of good that I'll tell you. And let's say each party is just going to find this function inefficiently in the pre-processing phase. Okay, so the quantum state that they're going to prepare is basically the commitment state to both 0 and 1. So the commitment state to 0 essentially consists of a uniform superposition of all the input-output pairs of this good function. So this, because it's lambda bits to 3 lambda bits, this is in total 4 lambda qubits. And the commitment to 1 is just a uniform superposition of basically any 3 lambda bit string, and that's the same thing for both the commitment state and the decommitment state. And this thing that does not actually depend on H. So, and actually you can actually just prepare this state efficiently. But let's say we also prepare some copies in the pre-processing phase. Okay, so, and then we're going to invoke the format that Barak mentioned to construct a commitment scheme. So in particular, to commit to bit 0 or 1, you're going to take either the 0 state or the 1 state, and then send the left half of the state as your commitment, and then hold on to the right half, which is what you are going to send when you later reveal the commitment state. So for a receiver to check whether this is the correct commitment, you can basically do a very basic quantum algorithmic procedure called swap test to test whether this state is equal to the commitment state to 0 or commitment state to 1, although this requires you to also have some copies of that state. Okay, so what we'll basically show is that if we just pick, in our paper, we show that if you just pick an H uniformly at random among all the possible functions, then this is actually good, meaning that it will actually make this construction work with overwhelming probability. Okay, so now let me quickly tell you what's the proof idea. So basically, okay, so and the more interesting case is the computational hiding. And I'm not going to talk about statistical binding. So to prove computational hiding, basically, we are going to see what's the receiver's view after the commitment phase. So basically, if you are committing to 0, then the receiver view is essentially a uniform image of this function h. But if you are committing to a 1, then you are essentially getting a completely uniformly random 3 lambda bit string. So the nice thing about this is that it's actually like a completely classical input that we are trying to prove the hardness for. Okay, so let's just define for the purpose of this talk, I say a function is good. It just means that if I do this in this commitment, it will be computationally hiding. So if you take a look closer, that just means that a uniform image of H is indistinguishable from a truly random 3 lambda bit string. And our goal is to prove that these are indistinguishable against any exponential size quantum circuit that can potentially even have quantum auxiliary input or quantum advice. Okay, before I tell you about the quantum proof, let me first tell you how you can prove this against classical adversaries. And this is actually already done by the work of Gorik and Krupchik in 1992. And they call this object sparse pseudo-randomness. So in particular, they prove that almost all functions satisfy this pseudo-random like relation where a uniform random image is indistinguishable from truly random Y. And this is true against all exponential size circuits. And the proof of this is actually not that hard, and you can probably assign this to a graduate cryptography or like randomized algorithm class as a homework. It's basically a standard counting or probabilistic argument. However, this thing is not too very useful classically, at least for crypto purposes. And actually, if you look at the proof closely, this actually generalizes to proving security even against quantum circuits. But that's only true if they don't have a quantum advice. So basically, the reason that it doesn't generalize is if you look at the proof, it's essentially using some kind of counting argument. So we are going to count how many different classical circuits there are of a certain size, let's say S. Then you can see that it can be equivalently expressed as some bit string of length S. So there are in total 2 to the S many different classical circuits. But if you want to think about quantum circuits with quantum advice, then it's possible that every approximately orthogonal quantum state will behave very differently from one and another. And if you look at the space of all the possible quantum states of size S, the number of different quantum states is actually doubly exponential instead of single exponential. And this naive strategy wouldn't work because essentially this exponential blow up is going to kill off your probabilistic argument. Okay, so in our work, we actually address this by doing a different proof strategy. Okay, again, the goal is we want to prove that almost any function h is pseudo-random against exponential size quantum circuit with quantum advice. So the way we do this in our two works is that we're actually going to treat this goal as like a random oracle security, by which I mean that it is already known that in the prior work, it was shown that if you take a quantum random oracle, meaning random oracle with quantum query, they are actually pseudo-random even against quantum non-uniform attackers. And basically, we can suitably adapt this proof to show that this is true even if you are in this quantum auxiliary input setting. And I should say that this proof actually uses a very general framework that can prove all kinds of non-uniform security in the quantum random oracle model. Although I should also mention that after we complete these works, Fermi Ma also told us that there is actually a way to adapt the Gore-Korchik proof. Essentially, instead of trying to do the naive probabilistic argument, you can apply a more sophisticated, but still pretty simple matrix Chernoff or Hofstee bound for the operator norm. And if you do that, you'll get a slightly better security. So you only incur the square root loss instead of the cube root loss that we prove in our papers. And this is actually like asymptotically the best security bound you can prove because there is actually a classical attack that achieves this achieves the leading constant. Okay, and if you are interested in this proof, I put this in my dissertation. It's not in our paper. Okay, so to summarize, what we prove is that we get quantum auxiliary input commitment unconditionally with pre-processing or quantum. Okay, so before I wrap up, let me also quickly mention some additional results. One concern that you may have is that, okay, this quantum auxiliary input is just some uniform superposition on classical state. Can we, is this the reason that we couldn't achieve this classically is because we are using deterministic preprocessing? Can we also gain an advantage using randomized preprocessing? So in particular, everyone can like receive a potentially different auxiliary input after the preprocessing, but they are not allowed to communicate. So in my work, I prove improved impossibility where I show that even in this setting, constructing a classical commitment would imply P not equal NP. So it seems difficult to actually dequantize this quantum auxiliary input commitment. And there seems to be something truly quantum going on. Let me also quickly mention another related setting, which is the secret parameter model. Here, if you are willing to trust the preprocessing a lot, like there's a trusted third party that does the preprocessing for both of you and can keep each of the secret from each other, and here we actually know how to do even statistically secure classical commitment. However, in their work, they also show an improved impossibility that if the correlation of these strings are small, then commitments remain impossible. And we also, on the quantum side, we also show that we can actually adapt our construction into this secret parameter model, but it's a much weaker trust on the third party. So in particular, we just need to trust the third party to generate the same state for everyone. And of course, the adversary can get polynomially many copies from this of this state. And we show that you can also get statistically secure commitments in this model. And you can also adapt the previous impossibility to show that if you replace this with a common classical distribution, you still couldn't do statistically secure commitments. Okay, so that's all for the talk. basically, we show the first demonstration of some useful cryptographic task, no matter classical or quantum, and it has the desirable feature of unconditional security. What's interesting is that this security is inherently computational. So I like to interpret this as a half full, half empty mentality. So if you are very optimistic, maybe you can say this is the beginning of unconditional computational cryptography, which could be exciting. But I think if you're pessimistic, maybe you also say that actually in our construction, the quantum auxiliary input is pretty inherent. So maybe you can only do this in the quantum auxiliary input model, but not the model without a quantum auxiliary input. But no matter what, I think what this shows us is that there is something interesting going on in the landscape of quantum cryptography, and we should definitely reassess whether computational assumptions are necessary for quantum cryptography, and we should also further investigate the existence of barriers. Okay, thanks.
Thank you, Barak and Leuven, for those great talks. Do we have any questions in the audience? Eli.
Is there any way to make the auxiliary state clonable?
Certainly, in our construction, you can probably prove that it's unconditionally unclonable. But yeah, it would be interesting if you can find something that can make it clonable.
So a quick follow-up is there a way to make it classical? I'm guessing not, right? That's
actually you can probably even prove some barriers. So okay. An interesting thing about our scheme is that this is actually relativizing. So this commitment would work relative to any oracle. However, you can show that for classical auxiliary input, there is some oracle where this is impossible. So making this classical has some barriers.
Thank you so much. We have another break, so if you have more questions, please feel free to ask Leuven outside.